Merci, Yvan. Good morning, everyone. So I would like to thank Yvan and Carlo for putting up this very nice workshop, very broad, many topics. I'm learning a lot. And so indeed, today my goal will be to try to tell you about classical and quantum spin liquids. So everything you wanted to know about them, I hope. And please do ask questions, because I apologize in advance, but I will leave right after the last talk today. So I will be, I will miss my discussion session. So if you have questions, this will be during the talk or during one of the break. I would be happy to answer. So, okay, to set up the stage, so we want to discuss some classical or quantum magnetism. So we'll be dealing with n spins. So we'll see, they can be Ising spins, they can be continuous spins. But to simplify, I mean, it's already very rich. We really want to focus on the spin properties. So I don't discuss any itinerant magnetism, which is very interesting for some applications like spintronics, because you have additional difficulty of the charge degrees of freedom, etc. So I only focus on the spin degree of freedom. So I will take them localized. We know this exists in many materials, so we'll discuss a bit about the platform. But for instance, yesterday also we had the lecture by Antoine Georges, where he showed that for this parent compound of the high temperature superconductors, when you have no doping, they are simply localized. The charge degree of freedom is completely frozen. It's also called Mott insulator. And then only remain the spin degree of freedom that can order. So I will localize them on a regular lattice. So we'll see a couple of regular lattice, but it's real life, so it will be 1D, 2D, or 3D, which is already quite a lot. We'll see. And also when you think about quantum dynamics, it adds some extra dimension. So in the end, it's a very complicated problem. And regular lattice, so this is also to avoid any disorder. So no disorder. We know disorder is very important. It also exists for sure in real life. It can lead for classical spins, let's say, to spin glass behavior, which is a very rich area and still not completely solved. Let's say about 3D spin glass. And when you go to quantum, disorder can lead to localization. So we know the one-body localization or Anderson localization, but the many-body localization is a very ongoing topic that Anatoly didn't discuss, but I mean, slightly discussed. So here, no disorder. So I want to avoid also these difficulties. And then, okay, so of course, n spins, but n large, so n going to infinity. So I'm not considering any molecules also, which are very nice for some applications, but we are interested in phases of matter, exotic phases of matter. So we want to discuss thermodynamic limits. So this is the hope, of course. I'm mostly a numerical guy, so we are very far from numerical, from the thermodynamic limit. But from the conceptual point of view, this is what we want to describe. And indeed, we know there was this famous article by Anderson, more is different. So we know that it's not because you understand one spin, two spins very well that you can understand what happens to n spin. And it can be very rich. In particular, what Anderson was pointing out is that we know that we are used to that in solid states. We have emerging properties. And this is one of the take-home message of this lecture. We'll have some emerging properties. And what kind of properties? So some keywords that we'll encounter very often. There are some gauge structure, which is not necessarily present in the microscopic. As a result, sometimes there is some fractionalization. There will be a lot of topology. So all this will be clarified, of course, during the lecture. Both in the classical and quantum case, fractionalization means, for instance, that excitation can be part of the microscopic degree of freedom. And we had the lecture on Monday about quantum Hall effect. So we see a lot of analogy with quantum Hall effect in this that can be realized with magnets. Okay, then I still haven't defined exactly. So why people are calling that spin liquids? It's simply some analogy. So we want to describe phases of matter. And of course, we learned that at the elementary school, middle school. Maybe that depends on the country, kindergarten, maybe. So we have gas is really for particles when there's no correlation, very dilute. In the spin language, this would be a paramagnet, meaning that you have spins. Okay, maybe this one no correlated. Okay, without any correlation. So like high temperature phase. So usually a paramagnet will be at very large temperature compared to the coupling constant. So I haven't defined any model yet, but we'll come to that. Then at very low temperature in normal matter, we have a solid. When the particles like form a crystal, spontaneously breaking some lattice symmetries. In spin, this can also occur, and it's called a magnetic order. And we have a variety of them. Of course, if all spins point in the same direction, this is called a ferromagnet. But we will be mostly interested in anti-ferromagnetic interaction. We'll see why. So this one will be an anti-ferromagnet. No, AF in short. And of course, you have many other orders you can think of, but this is not exotic phase in a sense, so it occurs in many models. We'll, of course, we'll have to mention, let's say, the 2D Ising model or this kind of model that explains this phase transition from the paramagnet to ferro or antiferro, so through a phase transition. And so in between, in normal matter, liquid is not really defined. You know, it's the same as a gas. So it shouldn't be too ordered. That's always difficult to draw. Because you know, liquid and gas are, in fact, the same phase. In water, you can go from one to the other without crossing any phase transition. They don't break any symmetry. So people discuss a spin liquid as a state which has no broken symmetry. But indeed, this one also has no broken symmetry, like liquid and gas. So in fact, spin liquid means more. So that's also the goal of this lecture, that everyone understand that. So they don't break any symmetry, but still they are non-trivial. And there will be some classification that I need to do, or that people are doing. Yes?
I was always curious. To me, like symmetry, any local unitary transformation which keeps spectrum invariant. But how can you rule out that all such unitary transformations don't exist? This definition of symmetry.
Yeah, but you will want, so this will be this like no-go theorem, like Lipschutz-Matisse that I will discuss. So there are some models, you know for sure that it's forbidden to have a unique ground state at the gap. So this is the kind of spirit. So this is you will see during the.
Oh, so absence of soft modes, basically.
No, but even if you have a gap, you need to have a degeneracy, and then you are left with breaking some lattice symmetries or topological order. But you will see it coming. And indeed, so precisely this is the point. So spin liquid is really non-trivial. Okay. Spin liquid is really non-trivial in the sense that, for instance, it can have critical correlation. You know, in liquids, everything is short range. Here we'll have example, we call them spin liquids, but they have power law correlation, algebraic. So which is very weird, and in particular, we call them critical behavior when it's algebraic because it's very fragile. And here you will see it's very robust, in fact. So we have a power law, but it's very robust. So these are some of the spin liquids. It can be critical correlation for the spin-spin correlation. Or it can be, so this will be this topological order. And then topological order, it opens Pandora's box because this classification goes very far. There are lots and lots of different topological orders. And so there will be some math, which I'm not really expert, but at least to describe. OK, so at least the name, spin liquids, think it like a liquid, so no broken symmetry, but in fact it's very different because it has non-trivial properties. Okay, maybe to finish setting up the stage, so what kind of models or... So this was a big introduction, and then there will be some parts. So the kind of models we are interested in, so we'll have Ising spins. So it's simply plus minus 1 or 0, 1 if you are quantum information. And the model is typically Ising model. Okay, let's say, for simplicity also, I will consider nearest neighbor or short-range interaction, because that's enough to describe most of the thing. But of course, when you want to describe real life, you may need some additional details. So we'll have Ising spins, or we'll have Heisenberg spins. So when you consider vectors classically, or operators, let's say SU2, I will focus on spin 1/2, spin 1 for in the quantum case. And this time the Hamiltonian, well, okay, depends if you are quantum or classical. But similar thing, except that you have some maybe operators or vectors. And vectors, they can be 2 components, 3 components. These are different names. Okay, so when can we, in fact, most of the time, if you think about a simple model, you will end up with some magnetic order. And the key ingredient for the spin liquids is so-called frustration. And frustration, it's a good name because it was called non-fitting initially, I think maybe by Vanier in his famous paper. It simply means that you cannot accommodate all interaction. And so suppose, in fact, so maybe I will show, so 2 of the founding fathers of the field. So for the classical, that would be Vanier in 50, who solved the triangular antiferromagnet. So antiferromagnet means J is taken to be positive. So for Ising spin, I want them to be opposite, let's say up and down. And this is the famous drawing. When you have one Ising spin up, one down, you don't know what to do with this one. Because whatever you pick, one bond will be disfavored. You cannot minimize. If it was ferromagnetic, you could get minus 3J. Here, the best you can do is minus J. Or, yeah. So we'll discuss this model right after. And in the quantum case, it's funny to say that it was also the triangular lattice. So it's really the test bed for frustrating magnetism. So Anderson, in his famous paper in 72 about resonating valence bond theory, considered the quantum case. So the quantum spin 1/2 triangular. And I'll give you more details when I do this part. But it's interesting because you say, oh, maybe this is a good candidate for not ordering and being a kind of spin liquid, which was one of the famous concepts in the field, which was called resonating valence bond, and that we'll see after. Okay, so maybe to finish this introduction, I won't discuss any experiments for lack of time, and I want to focus on the theory side. But let me just say that experimentally, so we have quantum matter, so we have materials, lots of materials, and we have also these cold atom, ultra cold platforms or Rydberg arrays that we'll hear maybe later today. So there are pros and cons for both platforms. We heard already in the previous days that cold atoms are very good control, which is nice because you will see that some of these models, they still need some fine-tuning maybe. So we have very good control. There is the issue of temperature, and there is also the issue of maybe some defects. Okay. So I won't discuss experiments, I say, but just to say that there are very good evidence of spin liquids. What people do typically is they measure the ratio of the so they measure the ratio of the temperature, the Curie Weiss temperature, divided by the ordering temperature. Because ultimately, the hope is that there is no order even at 0 temperature, but very often due to additional coupling, they do order the materials. But so this is the typical energy scale, and this is TC. Okay, and if this guy is very large, so Curie Weiss temperature, yes, Curie Weiss. So actually, we are close from Curie, Institut, etc. So it's simply in a magnet, when you are at very high temperature, if you plot 1 over susceptibility, magnetic susceptibility versus T, it's so for a free spin, it's just linear, but when they are interacting, if you do Weiss mean field, you get some T Curie Weiss here. And essentially, it gives you the J. It's a way to get J. So if the critical, so of course, yeah, maybe let's put some KB here. So this is energy, this is energy. So if the critical temperature is much, much smaller than the coupling constant, it means that something is trying to forbid order. So this is the experimental definition of frustration. And just to see sometime, if you go to some reviews, you will see this table with this ratio, and it can be 10, it can be 100 in some compounds. Okay, so the questions, they will be very basic. What are spin liquids? Because very often they are defined as what they are not. You know, maybe this joke like what is a non-Fermi liquid? It's like what is a non-banana? It's very negative. I mean, you cannot really say it's an. So if you say it's no order, indeed, okay, many states have no order. So we want to understand what they are. So as I said, they do have some properties. So this is the goal. Of course, can they exist for some model? So model for me would be just the Hamiltonian, classical or quantum. Yeah? Can they be stabilized? Even if it's fine-tuned, it will be I think it's very important in the field to have some exact results. Because at least conceptually, it tells you that yes, it's possible, it exists, and then you can look in microscopic models, which are more involved and need more advanced technique. But I think the main advances in the field was probably do some exact results. And a very important ingredient is the use of symmetry. And we see also for this classification business, it's very important. So it's like in high energy or many other fields in physics, symmetry is really a guiding principle. We rely a lot on symmetry. Okay, so let's start with a classical spin liquid. And I'll give you some examples. So the famous finding by Vanier in 1950, I will give you more detail, was simply so to consider this triangular AF with Ising spin plus 1 minus 1. So maybe let's do more triangle. So we see that we have some issues. As I said, this one we can pick. So we want to have anti-parallel spins on each bond. So maybe now we are happy if we do something like that. But we have some defect. So how many ground states? So it's the question he asks. and what are the correlations in the ground state. So it's a classical stat-mech problem, and usually we have only a finite number of ground states, but this frustration leads precisely to the opposite. So something which is very counterintuitive, that you have an extensive number of ground states. And without doing the exact calculation, which is like quite involved, using similar techniques as Onsager has used for the exact solution of Ising model in 2D. Yeah, by the way, maybe just a few comments about Ising, because we were discussing maybe sometime PhD topic. You know that Ising got his PhD by showing that the 1D Ising model has no transition, which was very disappointing result. But then the name was kept, and now we know we have transition in 2D and higher. And just to show, because it's a workshop about open questions, rigorously, not much is known, for instance, in the 3D Ising. And maybe you know, so Hugo Duminil-Copin got the Field Medal for showing it's continuous. So we know it's continuous, but OK, we asked him at a talk, can you show its critical point is conformally invariant? And he said, oh, no, this is very, very difficult rigorously. So there are many open questions, even at basic phase transition like this. OK, but so coming back to triangular Ising, so can we have a simple argument for number of ground states? It turns out we can. In fact, if we start from a honeycomb, so it's too bad I do everything on the board because I'm not a big fan of drawing, but that's OK. So honeycomb is bipartite. So bipartite means precisely, even if it's antiferromagnetic interaction, everyone is happy. You can really arrange, you can alternate like this. So you have two sublattices, you know. So A sublattice will be up, B sublattice will be down. Everyone is happy. And now you can, so, OK, this is honeycomb. Everyone is happy, but now I can add the missing site to go to the triangle. OK, I can go to the triangle. And now the nice thing is that here I can put any spin, up or down, on this, up or down. Whatever I do, it will be one ground state. Because you can check that on each triangle, there is only one unsatisfied bond, which is my condition for the ground state. This is the minimum I can have. It's frustrated. I don't want to frustrate the three bonds. I don't want three up spin on a triangle. So it's one ground state. So the number of ground states, for sure, it's a lower bound. For sure, so you can count. So how many hexagons like this do you have? If you have n sides, you have n over 3 hexagons. And for each of them, I can have up or down. So I know it's larger than 2 to the n over 3. So it's huge. What people measure, what people compute, is the entropy, which is simply so at zero temperature, we are talking about ground states. Huh? This is just the log of number of configurations. So the entropy per speed, or OK, maybe I can like this. So the entropy would be log 2 over 3 kBn. And if you want this number, so this is 0.231. So extensive. And this is very counterintuitive because there is a principle in thermodynamics which is called Nernst's principle, which tells you that entropy should go to 0 as T goes to 0. And so it's wrong in this model. And in many classical models, it's wrong. Nernst was not a quantum guy, I think. But no, I know. No, so in many classical examples, it's violated, while in the quantum world, we believe it's true. So extensive number of configurations. So this is a rigorous bound, very easy to do. If you want an approximate, there's another famous approximation by Pauling, who had 2 Nobel Prizes. And so Pauling did this for the water ice. Actually, I will come back to ice also in a moment. But Pauling did this simple approximation. He said, OK, suppose the constraints are independent. What I'm throwing, so I want to remove the configuration where all the spins are up or all the spins are down. Suppose you just look at the up triangles in the triangular lattice. So you look at all of them. So there are n of them. And so on all up triangles, so usually you have 3 sides. So you have 8 configurations with up and down. But you want only to keep 6 of them. So the counting would be, OK, so this is approximately, so you have 2 to the n configuration, but you have a deflation factor 6 over 8. You see the counting? So 8 configurations on triangle, I remove 2 of them. And this, again, this is an approximate number of ground states. So of course, you suppose that they are all independent, and they are not. So it's not a controlled approximation. It's probably an upper bound, because you suppose they are independent. And if you do that, you also find entropy, which would be, so there's S KBN. We just want the number. We find 0.4, I think, log of 3/2. But OK, maybe we don't need the approximation, because we have a lower bound. And the nice result, maybe, so I can show, because it was the point of Vanier. He managed to do the exact calculation, and you get 0.3 for the entropy. I mean, some complicated integral, but you can compute exactly. OK, so maybe it will be interesting for some of the model I want to discuss to also show that there is a mapping to other class of statistical mechanics ensemble, which are dimer problems. In fact, again, maybe we need to draw some configuration. Something like that. So we draw a configuration. So hopefully we try to. So we just simply forbid 3 up or 3 down on each triangle. And now we look on the dual lattice. So the lattice where you put the sides at the center of these plaquettes. So it's the honeycomb lattice. Hexagonal lattice. And each time you have a disfavored bond, so there's only one per triangle, you draw a dimer perpendicular to it. So here we had 2 upspins. So we draw, like say, an object like this. So this object is a dimer. It has no orientation, it's just a rod. Similarly, here we have one like this. Here this was maybe this one, and here it was maybe this one. So you can see that the number of ground states is the same as the number of packed dimer, dimer configuration. Fully packed. For the expert, fully packed dimer, so meaning really, you look on the dual lattice, on any graph, you can ask a question, can I put dimers so that every site belongs to one and only one dimer? And this is a classical also stat-mech problem. And this counting problem is solved by since the 50s also by Castelline and then Fischer. Castelline. There is a solution for planar graph. So of course, when we draw 2D, we say, okay, they are planar graphs, so we are very happy. So it means we have a solution for the dimer problem, or honeycomb, triangular, whatever you like. Let me mention that, because we want to discuss some open questions. So this is an open question. No exact solution. When adding longer range. Okay, so usually we denote them with J2, J3 means coupling to second neighbor, third neighbor. And for instance, if you take another lattice, there was a very nice work in the group of Frédéric Millat, Jean Colbois. So this is a very famous lattice we'll also encounter maybe later. We start with David like this. So it's called the Kagome lattice. Comes from Japan. There was a traditional way of designing some shapes. Oh, sorry, Kagome is written twice. That's maybe too many. So you can play the same game I just did. You can ask the question, what about Ising model on Kagome? You see maybe there are less frustration, but you can try to do that. And so it has, again, an extensive entropy. But it has short-range correlation. Oh, yes, actually, I didn't mention, but for the triangular, so not only you can count, but you can compute the spin-spin correlation. So maybe I can add it also. Spin-spin correlation are power law. I never remember if it's 1/2 or 2. Maybe it's 1/2. Not sure, but power law. Which, as I said, is non-trivial. When you think about it, if you just look at this, you say, oh, it's very disordered. I have an extensive number of configurations. What are the correlation, extensive number of configurations? So I expect maybe short range, but in fact, no. They are power law, and for some good reason, because there is a gauge structure.
Does power law disappear immediately at finite temperature?
That's a good question. So I mean, there is no order anyway. There is no order at any temperature. Yes, there is no order at any temperature. Okay, but just an open problem, I say. So for if you start adding some J2 would be like this. So J2 would be second neighbor. So maybe this is J3. So maybe J2 is this guy. J3, you have several of them. So that depends maybe a bit on the model. Maybe J3 would be a coupling like this. If you start asking the question, what are the number of, again, very simple, Ising model. What are the number of configurations for some particular, when you play around with these parameters? And it's very complicated to do. It's a classical model. So sometimes I'm a bit provocative. I say to classical StatMech is completely solved. We have Monte Carlo. We know how to do everything. It's very complicated because Monte Carlo, you will have freezing. It's very difficult to access the ground state. So people, in fact, are using tensor networks. Because maybe you know, or actually it was also Baxter who invented that, but a partition function can be written as a contraction of a tensor network. Actually, the 1D solution of Ising that you all do in class is just a contraction of matrix, like a trace of some transfer matrix to the n. It's very easy, you solve the matrix. In 2D, it's not a matrix, it's a tensor. And contracting tensor networks, we have good algorithm, but it's much more complicated. So, okay, just to say there are open questions. People are using very sophisticated techniques. So this was for Ising, but I'm going to dimer or vertex model, where the variable they live on the links. And that's where we start touching that we have maybe connection with gauge theory. Because in the 70s also, people were, and are still working. Suppose you put variables on links, It's a very natural formulation of gauge theory. And so indeed, if you do one of the famous models is six vertex from the square. Actually, it's also called square ice. So we'll talk about ice now. So it was solved by Baxter when you put some complicated model, let's say statistical mechanics, but you put some energies to the configuration. But the rule, why is it 6 vertex? Because so the variables are on the link. So I can, instead of putting +1, -1, I can put arrows. And the rule of the game is to have 2 in, 2 out. Okay, so maybe we need to draw a lattice. Huh? At each vertex, I want to have 2 in, 2 out. And you can play, there are lots, so I put 2 in, 2 out. Okay, you can play around and draw configuration. You see the rule of the game? 2 in, 2 out. How many configurations? Number of, it's just a counting problem. Then you can do more complicated stuff, like solving a model when I give you an energy for some vertices, etc. So first of all, it's clearly 6 configurations per site, because 2 in, 2 out means I have to put 2 in arrows on 4. How to pick 2 on 4 is 6. Okay? So that's why it's called 6 vertex. Number of configuration, again, it's not a simple problem, but we can use Pauling estimate. And let me tell you the story, actually. So because it's almost a century ago, people were interested in water ice. So the water ice we love in summer. So water, it's the usual form of water ice. It's on a diamond lattice. And there are some chemistry, covalent bonds, blah, blah, blah. But at the end of the day, it means that 2 of the hydrogen are closer to 1 oxygen rather than the other. So it's like 2 in, 2 out also. So you have 2 hydrogen close and 2 are far. And how do you distribute that? It's the same kind of counting on a different lattice. But at the end, it's the dual of the diamond is a pyrochlore, which I will try to draw later, but it's made of tetrahedra in 3D. But you want to count 2 in, 2 out. So it was measured experimentally. There is residual entropy. So you really do thermodynamics. You measure specific heat, you integrate, and you have this beautiful experiment by, I forgot the name, Gauke, by 1930. And so people wanted to understand that. And so what Pauling did was this very simple and crude estimate. You say again, OK, I have, so we can apply here to our model, but it's the same for the pyrochlore. So now we have, if n is the number of sites, we have 2n degrees of freedom, okay, because for each side there is a bond to the right, a bond to the up. So naively, we would expect this number of configuration, 2 to the 2n, if I put arrows everywhere. If I suppose that my constraints are independent, which is not controlled, the deflation factor, I need to keep only 6 configurations, the 2 in, 2 out of 2 to the 4, which is 16. Okay, naively, at each site, I have 2 to the 4 configuration. And this is beautiful because it gives you almost, for water ice, it gives you almost the exact result because this number is so log 3 over 2, which is close to 0.4. So experimentally, water ice was measured, but you could say, oh, maybe it's an experiment. But for this model, which is simpler, there is an exact solution by someone famous, we have heard many times, by Elliott Lieb. He could compute that exactly and show that this entropy is 431. So you see that, OK, 10% error, but doing a very crude approximation compared to a very involved calculation. OK, so these are the kind of model we also like. And not only we like them, but they do exist. As I mentioned, so the material, or the same rule would apply, is the pyrochlore. So it's complicated to draw. As I said, it's made of Hydra. So that's probably the best I can do, but you can go to Wikipedia, anything. You just look for pyrochlore. So it has a 3D structure. It's one of the lattice. It's realized in many materials. And for some reason, for some material, so which are called actually the spin ice. Okay, you understand this rule? Ice simply means that it comes from water ice. You have this 2 in, 2 out. 2 in, 2 out. And the nice thing about this, what has been very popular in this field, is that when you do a very simple coarse graining approximation, okay, you have a local constraint. And we know a field where local constraint is important is electromagnetism. When you say that you have a divergentless field, this kind of thing, it's a similar rule. Because you see, if you think this is a kind of flux, you have a conservation. Or if it's a current, it's like when you do a problem with electricity, okay? The sum of the incoming current are the sum of outgoing currents. So you have a local constraints, and it means that you have, when you coarse grain, you have an E field or B field. Actually, they were clever. Instead of choosing electric field, they choose magnetic field. At this stage, it's the same, because you can pick any field. But it's just that, let's say, so let's take B. So divergence B is 0. OK, so we have to hide this one, I remember now. So divergence of B will be 0, which is simply enforcing this local constraint. And then you want to write an action, and the action is the electromagnetic action. So suppose you take B, it will just be B squared, proportional to B squared. And then you know everything, or E squared if you prefer. You know everything. Correlations are dipolar. So we had this nice lecture about dipolar gases, so I don't want to repeat the formula, but you know dipolar correlation have this orientational, very peculiar form, delta mu nu minus q mu q nu over q squared. It gives rise to very sharp signatures in a structure factor, because at the end of the day, you want to compute spin-spin correlation that you can measure in the lab. So equivalent to dipolar correlations are so-called pinch points in the structure factor. It means you have, because of the dipolar nature of the correlation, it has very anisotropic behavior also in Fourier space. If you go along some direction or perpendicular to it, you have very different response. And this was measured, and it gave to the, yes, so this is the famous spin ice story. And why I say that they were clever maybe to pick B, because now when you have a defect, so suppose I flip one arrow. Suppose I flip one arrow. So now I'm violating this guy and this guy. But if I continue flipping, I can restore here if this guy is also going down. But now I will be violating this vertex. And I can go on, go on, go on. It means that if I make a local excitation, it will fractionalize at no cost. These guys are called monomers in the dimer language. Here they were called monopole, but these monopole are deconfined. So maybe, yeah, okay, I will take another board. Monopole defects. And that's why they were, there was such a buzz. It was quite successful because experiments were explained in terms of monopole proliferation, etc. But it's a very natural language. You have a local constraint. So it's a gauge theory. You know, electromagnetism is the first gauge theory in physics. Okay, so we know that gauge theory can really occur even for classical systems very naturally. So local constraints mean gauge theory, and here the gauge theory is simply electromagnetism, or electrostatic or magnetostatics, and so defects are monopoles. Okay, maybe let me. So of course, I only discuss simple models, but when you want to consider materials, this is maybe even dipolar interaction, so it's not short range. Maybe you have to work a bit to argue that it's valid, but you can do it. Maybe, but quickly, because time flies. What about for continuous spin? So I'm still in this classical part. So I'm just thinking about O3 spin. Okay, so S is a vector. And in many systems like corner sharing lattices. So actually, we had the Kagome before. So you see they are made of corner sharing triangles. So this is Kagome. Another one, if you like to play, is the checkerboard. If you like to play chess or checker. Something like that. It's kind of flattened tetrahedron for 4 sides all coupled together and sharing corners. So the Hamiltonian up to a constant is simply sum over this plaquette, total spin on the plaquette square. Because if you expand the square, you will get S dot S, S dot S. So it means within a plaquette, all spins are coupled together with the same coupling. And then it's very natural, you want to minimize. It's simple. You want to enforce classically, you want to find vectors that arrange such that the total spin is 0. But if you start playing the game, so on a triangle, it's very easy. It's the so-called 120 degrees order. But now you see on the Kagome, it's still very frustrated because once I chose this one, I still have many freedom for this one. Actually, I can go the opposite, chirality, I can do something like that. It's still a sum of 3 vectors. Here I can decide to do that, or I could do the opposite. I have a lot of freedom. So again, there is a counting, which is a problem of counting constraints. And actually, the counting is due to Maxwell when he was asking the question, if I have a rigid body, how can I fix it? If I have some solid, in how many places should I put a nail to really fix it? So this is Maxwellian counting. So you count number of degrees of freedom, you count the number of constraints, etc. You assume they are independent. And you can do this for this exercise. And you find that most lattices that we are interested in, they still have extensive degeneracy. Why it's a bit more subtle than easing? Because it's not just counting, because of course you have continuous spin. So even if I have a unique solution, let's say on triangular lattice, suppose I take this one. And so this guy is probably, yes, like this. And this is like this. So it looks like a unique configuration, but I can always rotate. If it's a vector, I can rotate in all directions. It's SO3 invariant. But I don't want to consider this symmetry. I want to know whether I have additional freedom. So you can do the counting. But OK, I won't do that. It's very, very similar. And you can argue that some of these lattices will be frustrated in that sense. Maybe just to mention, because I am drawing the triangular case, there is an open question. There is an open question because at finite temperature, for the triangular case, you can have, and suppose that spins are, spins, they can be O3, they can be O2 also, they can be in the plane. So in the plane, this is the famous XY physics. And maybe you know there is a Kosterlitz-Thouless transition at finite temperature. But so here you can break a U1 and a Z2, the chirality, because I can decide to go clockwise when I take an up triangle, or I can go anti-clockwise. So I have some, let's say, O2, U1 cross Z2. symmetry. Okay, this is chirality. And so an open question in the field is whether these two symmetry or two critical temperatures, so the Costerlitz-Thouless and the Ising, so this one should be Costerlitz-Thouless, this one should be Ising, whether they coincide, whether they are, okay, well, what is the scenario for this finite temperature phase diagram? And again, it's a classical problem, so you can do Monte Carlo on 10 to the 4 linear size, I mean, huge system, but it's still not completely solved. And maybe now I will end the classical part by telling you something about classification. Actually, I will only maybe discuss this continuous spin case. But it's quite simple, at least to explain the idea, to give you a flavor of what we need to do. So it's based on Luttinger-Tisa approximation. It simply means that if you go to Fourier space, which is what you want to do to solve this problem, if you go to Fourier space, you will get S mu. So this is an M by M matrix. And what is M? M is the number of spin per unit cell. So meaning, if I have a Bravais lattice, then I'm very happy. So let's say triangular lattice is a Bravais lattice. So in fact, it's very simple to solve this model. I simply Fourier transform by Heisenberg Hamiltonian. So now it's not a matrix, it's just a number. And I just minimize. So maybe I will call it J of Q, but it's a matrix. So I will simply minimize J of Q. Okay, so Q is a vector. Okay, I mean Fourier. I will simply minimize J of Q for Bravais lattice. And here I immediately get this order. This order, okay? Now if it's non-Bravais, there is no easy way. You would like to minimize, I mean, you need eigenvalues of this guy, but here, in fact, this Luttinger-Tisa approximation, the constraint, in fact, you are taking a weaker constraint, which is that the sum of S I square over all the lattice is n. But what you really want is to have a fixed spin length. Each vector is of a fixed length. Okay, you want a strong constraint. You want each side to have a unit vector, let's say, but you have on average. This is the only thing you can treat. So it's not completely clear. You can do this approximation, you can solve, but maybe the minimum will not be achieved in the real microscopic model, etc. So you have to work a bit, but essentially the classification is based on this J of Q. And there are many groups working on that. I think it's still not completely in progress, I will say. If you know a bit about also topological insulators, this kind of thing, it's a bit similar because so this matrix, actually it's made of a constraint vector. If you look at the constraint vector over Q, it can have some flat bands, it can have dispersive modes, it can have some gap closing points, and this is what you want to classify. How many gap closing points? So the pinch points. How many pinch points do you have? Do you have 4? Do you have 8? This is how you classify. Okay, so you can classify number of pinch points, number of bands, what about the gap, etc., etc. So it's like this classification of topological insulators. Okay. So I think this is all for the classical case. And now we move to the quantum. So, of course, all spins are quantum. Yeah? Even when I was talking about classical, what I meant is that quantum fluctuations were negligible. But everything is quantum from the beginning. So quantum is simply when quantum fluctuations play a role. So there are many ways to add to the model. If you are thinking about Ising, so now it's an operator, it could be, for instance, sum over, so what we add, the sigma z term. But now maybe you can add some sigma x. So this is the famous transverse field Ising model. It has very, in some case, you can solve that in 1D exactly. It has a phase transition in the Ising universality, etc. Or you can also go to Heisenberg, let's say SU2. When you promote the vectors to SU2 operators, and the total spin will be 1/2, 1, etc. And of course, what people do sometimes in the field is to add dot, dot, dot in the model, meaning that if we add second neighbor, if we add spin chirality, if we add, of course, it's a different model and we have to work. But this is we can play, of course, a lot with the model to try to stabilize some of the exotic phase. So the starting point for the quantum, as I said, is the seminal paper by Anderson. So it's at 72, maybe it's 73, okay, I never know. And it was called resonating valence bond theory. So he was thinking that, okay, quantum mechanics is in fact a natural playground to destabilize order. If you just take two sites, okay, if you have classical vectors, this was more the idea of Néel. If you compute the energy, now it's just SZ, let's say, so it's spin 1/2. It's a spin 1/2, so the energy will be 1/2 times minus 1/2, minus 1/4. But now, in quantum mechanics, we know that if we couple two spin 1/2, antiferromagnetically, the lowest state is a singlet. Total spin 0 when you couple to spin 1/2. So be careful, it looks like a dimer, but it has some orientation because the singlet is antisymmetric when you exchange the particles. And this is also very simple to compute with this S dot S. And it's way better. It's minus 3/4 of J. So already in 1D, if you take 1D Heisenberg, which is one of the few exact results we have in the field, so it was the famous solution by Hans Bethe, 1931. The ground state energy is 1/4 minus log 2, but okay, maybe we just want the number. It's close to minus 4/4. So you see, it's already not too bad if you just make a singlet. But then, of course, the trick is if I take a singlet, then the next bond cannot be a singlet. Oh, because, yeah, you could say maybe it's even too low, but no, because the best I can do for a variational state on the chain, I could do a state like this. But then energy per site would be half of this. So minus 3/8, so 0.375. But I'm not too far. And so Anderson said, okay, maybe for the other lattice, let's go to 2D. We don't have exact solution. We have a semi-classical order, so we can take this order and promote it to the quantum world, do spin wave, this kind of thing. But maybe it's a competitive state. And so for the triangular, you say RVB would be, so it's more difficult to draw now because it's a superposition of this kind of singlets. it's like a soup. So we know in quantum mechanics when we start doing superposition, we gain some energy. So this was the idea. And in fact, this idea was very good, but forgotten because, okay, that's life. At the end, the triangular spin 1/2 is believed to be order. It's not proven, but all the numerics indicate it has some long-range magnetic order. And the idea was revived in a different field, like when the ITC started in 1987. Because RVB, if you think about it, when you start doping, it's a natural, it's a good playground to promote superconductivity. Because when you start putting two holes, maybe they want to pair because you prefer to remove only one diamond. So that was the idea, and then it was revived and very popular, and people started again thinking about RVB theory, and can it be realized in magnets, simply. My talk is only about magnets. So I will show you that yes, it does exist. So spin liquid exists, at least in models, both in the classical case and quantum case. So again, so we are in this quantum part, but we still have the same questions. What are spin liquids or what they are not? So we know they don't have break any symmetry, but maybe I will try to answer Anatoly's questions. Do we have some constraint? And they have something. So in particular, now we are quantum, so we can ask whether they have entanglement properties. So we see that topological phase have, in principle, a clear signature in their entanglement spectrum or entanglement entropy, that I will define. And it's very analogous also to fractional quantum Hall effect. For this topological phase, we want to see if they have fractionalized excitation, if they have a gauge structure, etc. And essentially, we want to find exotic phase, meaning they are phases which are not connected to product state. So this is why and what I will try to address now. Okay, so we are doing many-body quantum, but we want to look at, for all the quantum part, we want to be at t equals 0, or very small t. Why is that? Because, again, even for the non-frustrated case, let's say 2D spin 1/2 square lattice, it's not proven, but it's believed to be ordered at 0 temperature. But because of Mermin-Wagner, as soon as you put temperature, it's disordered. So it looks like spin liquid in our definition that is no order, but simply due to thermal fluctuations. So I didn't discuss also in the lecture order by disorder, actually, but when you have this very large degeneracy in the classical case, when you add thermal fluctuations, or when you add quantum fluctuations, Villain has argued, so it's called order by disorder, that generically you reduce the degeneracy. This degeneracy was a bit artificial. Okay? It was not in the symmetry of the model, it was a bit artificial, so probably any kind of fluctuations will select a manifold which restores only the symmetry of your model. So disorder by disorder. So we know that thermal, so that's why for the classical case, I was mostly concerned with 0 temperature. And quantum case as well, because we already have quantum fluctuations that can do something, so we want to control a bit. Okay, so because we want 0 temperature and we are doing many body physics, we want to probe long distance properties, it means low energy. So we just want to have a look at the low energy spectrum, many body. And essentially there are 3 cases we want to discuss. So let me do this 3 drawing for the many body spectrum. So we'll do the same as here. So we can have a unique ground state and a gap. Okay, these are energies. We can have degeneracy plus a gap. So this is a gap, finite gap. These are total energies, many body spectrum. Or it can be gapless. So these are the only thing you can think of, okay? If you have a gap, you simply want to know whether ground state is unique or not. And now, to answer Anatoly's question, so there has been a lot of progress. Actually, it dates back to Lipschutz-Matisse, 1961. They show that in 1D, local Hamiltonian, in some sense, but everything is local in my talk, I said. If you're in 1D, local Hamiltonian, the case A, or AI, sorry, case I is forbidden for half integer, okay, let's say for spin 1/2, half integer per unit cell. So that's a very deep statement, in fact, if you think about it. So this is forbidden in 1D for spin 1/2. It means you can have that or that, that's okay, but this is forbidden. And it was extended to any D Is it any D? Yeah, I think, but okay. At least 1, 2, 3 for what we want. So it was extended, so not rigorously by Yoshikawa in 2000, and then more rigorously by Hastings, 2004, and maybe even more rigorously by Lachtergele. Okay, but it's really also an ongoing thing. Why is it ongoing? Because in all these first proof, they only consider what happens with translation. Okay, for instance, in 1D, this is the only possibility you can have. So this is forbidden, so you can have that or that. This would be, for instance, the spin 1/2 chain. It's gapless. It has an exact solution, we know. And this would be a chain where you break translation symmetry spontaneously. That's allowed at 0 temperature in 1D. You can break a discrete symmetry, and you will be in this situation, but you break translation. So only translation was considered. But in 2D, you can have topological order. And in fact, so there are many more constraints. And so maybe not even, and more constraints. So in my lecture notes, I will put, of course, all the reference. But for instance, on non-symorphic lattice, so we have experts in the room who are continuing that. But on diamond, pyrochlore, they are non-symorphic. So it only occurs in 3D in some lattice. So non-symorphic means some symmetry operations are not simply translation times point group. In 2D, all symmetries you can think of, you have some translations, and then once you have done translation, you can rotate, reflect, whatever. In 3D, you have, like, the screw symmetry. So you need to rotate at the same time. And okay, so they are very, and then it provides more constraints. And for instance, this pyrochlore, it has think about spin 1/2, it has 4 spin 1/2 per unit cell. So this theorem doesn't apply. Okay, it only applies when you have an half integer spin per unit cell. So it doesn't apply, but there is a refined version which applies. So it's impossible to have a featureless. So this guy is called featureless, because most of the time you can connect adiabatically. So my definition of phase is always, can I make adiabatic transformation from one to the other without closing the gap? So if you have this situation, you can probably completely remove this guy and go to a trivial product state. So that's why they are called featureless, or not very interesting phase. So it's very important, coming back to your question, Anatoly. So for instance, pyrochlore, it's forbidden. So either we break some symmetries, or topological order, or gapless. So a spin liquid, that's why topology will play a role. Huh? We don't want to break any symmetry. So we see that these are two possibilities. Either you break, let's say, lattice symmetry, or you have a topological degeneration. And we have people in the room trying to continue this. But how many groups there are, Shunxiao? 300, 400, okay. 200, okay, 230 to one by one. Okay, that's a lot of work. So you should be realistic for that. Okay. Actually, when I say that featureless are not interesting, what I found interesting in the field was that sometimes, okay, suppose you have this theorem doesn't apply, so it's possible, but can you find a wave function? Can you find a model? And sometimes it's not trivial. For instance, honeycomb. Okay, honeycomb, I drew some honeycomb lattice, hexagonal, so you have two sides per unit cell. So the total spin per unit cell is integer, so the theorem doesn't apply. So everything is possible. So this is possible. But if you think about simple Heisenberg, spin 1/2, they will order because it's bipartite. So this will be that. When they order, you break SU2 symmetry, you have Nambu Goldstone mode, so it's gapless. But this is possible. So can you cook up a model that realizes that? And so this was done by Parameswaran and co-workers. So I think it's important in this, but this no-go theorem is really what is pushing the field. Now we want to focus on this to find spin liquids. But let me mention, so yeah, how much time? Not so much. Okay, so maybe, let me see what I want to discuss. Okay, so maybe I don't discuss the trivial case. I just mentioned like this, but so case. Just for the record, so actually it's not interesting, but yeah, it was a bit, maybe a bit too much, because in fact it is quite interesting. Huh? So Haldane got partly the Nobel Prize for his famous conjecture. So if you take spin 1, 1D Heisenberg, so very simple model. It was so-called conjecture, although he doesn't like it to be called a conjecture, because to him it looks like rigorous. Oh, it's not rigorous, of course. I'm joking, but it has been confirmed, let's say, to the best extent, but there's no exact solution, that it's indeed something like that. So if you take periodic boundary condition, you have this feature. So you have the famous Haldane gap, a unique ground state. Now why it's already not so trivial, it's because in fact, if you take PBC, you have a unique ground state. If you take open boundary condition, you have spin 1/2 edge. So there is a notion of fractionalization. There's no spin 1/2 in the model, but you can even measure them experimentally. So the best picture was provided by AKLT, Affleck, Kennedy, Lieb, Tasaki. It's a modified model for which we can construct exactly the ground state. And each spin 1, you can say, you can view it as 2 spin 1/2 symmetrized. So it's a virtual. It doesn't exist, okay? It's just for the sake of mathematics. You say my spin 1 is 2 spin 1/2 symmetrized. That's perfectly correct. This is the Hilbert space. You make the product of 2 spin 1/2, you have 0 plus 1, but you symmetrize. So this symbol means symmetrization. So it's a perfectly genuine wave function. And now the trick was to make some valence bond again. Let me stop here. So I take an open chain. Now I do a valence bond. So this is a singlet. Okay, suppose you are able to write this wave function down, like you can. It's a matrix product state with a very small matrix. So you do all that. You do this recipe. You construct the spin 1/2 artificial stuff, but then you make them singlet. And at the end of the day, you get a free spin 1/2 on the edge. And this phase, so they have very peculiar properties because it has been measured. You can really view this fractional excitation, which is localized. It has some feature if you look at the entanglement spectrum. So maybe I won't define entanglement, entropy, etc. But it's a pure state. So you can trace over half of the system, get the reduced density. Because there is no spin 1/2 degree of freedom from the beginning. Your model is a spin 1 model. Yes, yes. And this phase is called symmetry protected topological, or SPT in short. SPT. And classification of SPT has been done in 1D by Wen and others for SUN symmetry. So we'll hear about SUN in the next lecture. I'm also very interested about SUN. So this is the only topological order you can get in 1D. So in this Wen's terminology, it's short range entangle. It's not the super nice topological order, long range, like fractional quantum Hall we would like. It's impossible in 1D. If you don't, it means that if you don't impose any symmetry, I can go continuously from this guy to a trivial state. If I impose symmetry, I cannot. Because you see, I have some edge states. Because it's a spin 1/2, it transforms projectively. Like, suppose I keep time reversal symmetry. You know from Cramer's theorem that you need to have degeneracy of some levels with time reversal symmetry. So it's a kind of protected, as long as some symmetries are imposed. You can do the same in 2D. I don't discuss that. You can have, so okay, gapless, it can be simply due to Goldstone mode. So this is a normal ordered phase. We don't discuss that in the spin liquid. But we are interested in the symmetry break, in the degeneracy. So the case, so several possibilities. You can have symmetry breaking, spontaneous symmetry breaking of lattice symmetry. And we have example in 1D. So I already drew this picture. So for spin 1/2, if you have some J1 and some additional J2, there is an exact solution by Majumdar and Ghosh. If we go to 2D, so this would be 1D. If we go to 2D, we don't have exact solution except for some cases where we have magnetic field, but I don't want to discuss magnetic field also. But we have good evidence, let's say, for formation of plaquettes, spontaneously on the square lattice. So you do break lattice symmetry for some model or additional interaction. But okay, these are not spin liquids because they do break symmetry. Okay, so it's not what was. So what I want to discuss, so which port is that? What I want to discuss is the topological case. So gapped. So topological gap phase. So I want some degeneracy like this plus a gap. So maybe first I will, yeah. So they do exist in some models. So historically, the first models were quantum dimer model. I already introduced the dimer model, so I just need to add quantum fluctuation. So this is the model proposed by Roxar and Kivelson, which is simply a local term. So I will count. So maybe I will do the triangular lattice. So I will have, now I have some Bryan ket, I'm doing some quantum mechanics. So I will count let's say, the flippable plaquettes, so the plaquettes where dimers are parallel. And I will add some kinetic term. So like in the part model, we call it T, because it comes from tunnel effect. So I will just flip. Plus Hermitian conjugate. Okay, so this was the classical problem we discussed in the classical part, just counting configurations, putting maybe some energy when they are parallel. So it's a classical stat mech. Now I have quantum fluctuation. And this model, let's say if you're on the triangular lattice, or if you're on Kagome, if you're on Kagome, you need to add some extra terms because it's not ergodic otherwise. But okay, I will also provide reference. We are at 0 temperature, so the only parameter is the ratio of these two coupling constants. So the exact solution when both are equal, this is the Roxar-Kivelson point. So the ground state is the sum of all configurations. It's the equal weight superposition of all configurations. So it's very much like RVB. Difference is it's not SU2, it's really a dimer. But okay, you can cook up SU2 model which have the same physics. And now because I'm on a frustrated lattice, non-bipartite, it's I can see topological sectors. So now maybe I need to draw a louder. Actually, we can just look at the one term. So let's take some dimer configuration like this. Suppose you have a line. Okay. You can take periodic boundary condition or infinite lattice. So you have a line and you count the parity of dimers, number of dimers. So +1 or -1, or 0 or 1, the parity. Is it even or odd number? And what you see is that the parity is conserved by the quantum dynamics. Because so here I have, let's say, 2 dimers, but when I flip both, I go to 0. So the parity is conserved. And so if you are in 2D on a torus, you have 2 parities. So it's called a Z2 number. And so this phase, there are very good arguments from the field theory that this phase is stable. So this was like a classical state. It's a quantum state, but all correlations can be computed also by classical tools. But it has a finite extension. So there is a Z2 RVB up to somewhere. And then there are probably maybe many others, but there are crystal phase. So that breaks lattice symmetry. So we are not interested in that. But what is interesting is that we have a Z2 RVB phase. So it was shown for quantum dimer model historically first. So there is some RVB. So here, everything is short range, okay? Short range correlation. So you do have a gap. But there is a topological degeneracy because you have one ground state in each sector. Yes, actually here you get non-flippable, so 0 energy state. And there are extensive number. And then the breakthrough, so it was known that in quantum dimer, which are a bit maybe more exotic, the breakthrough was when Kitaev proposed not 1 but 2 models. with topological order. And actually, maybe you heard, but because we are in the Poincaré Institute, he just got the Poincaré Prize 1 week ago, I think, so for his work. I didn't see the official announcement, but probably it was partly due to these very famous models. So let me maybe write down the models, but you can find the solution. I mean, this is some work, but this is some very nice exercise to do. So the first model is the toric code. So I will define some spin 1/2, and so the model is simply maybe minus sum over all sides of A site minus sum over all plaquettes B plaquettes. So let me write and make a drawing. So this will be the product of sigma x, and B will be the product of sigma z. And the thing is that so the AS will be, when you consider a site, you take this kind of cross. Okay, so you make the product of sigma x. And the plaquette operator will live on plaquette. And the variables are on the links. So it is some simple algebra to do to check that they all commute together. So the A's commute between themselves because they always share two sides. So the A's and the B's, so they are operators, they all commute. So the minimum energy states will be when they are all +1, let's say, because I put some negative sign. And it was exact to solve that. He was able to solve that exactly. And what you find is precisely this kind of phenomenology, namely that if you think about excitation, they cost something, because if all the A's and B's are 1, when I will make one defect, I will go from 1 to -1, so it will cost a finite energy, 2. But I have some different ground states. If I am on a torus, I have this degeneracy that depends on the genus of the manifold, etc. So it's a topological phase. So it's a gapped topological phase, which is Z2, because again, in the classification, when you look at the number of excitation, so the elementary excitations, there is a defect in the A, which is called electric, there is a defect in the B, which is called magnetic, and there is EM pair, which is a fermion. So the E and the M are the elementary excitation. They are boson, but they have a mutual pi shift. So you know maybe about topological phase. What is important is to know the braiding, what happens in the word line of these particles. So that's why you can do, but we have experts in categories who are doing even more complicated stuff. So now there are many models in the same vein, which are called string net models. So essentially you can construct any topological phase you like using a similar recipe. Okay, so this is for the maybe what was not enough. Why people don't stop at this stage? Because they are anyons. These are 2D. You can have any kind of statistics like quantum Hall effect, but they are abelian anyons. So it's not what we want for applications. Okay, maybe show more maybe, but the other model by Kitaev was done on the honeycomb. But now you need 3 colors. So on the honeycomb, you have 3 types of bonds. So let's say you have the X bond, you have the Z bond, and you have the Y bond. And now what you will do is to put on X bond, so the Hamiltonian will be simply minus Jx. On the X bond, you will put sigma x, sigma x. On the Y bond, you will put sigma y, sigma y. And on the Z bond, sigma z, sigma z. So it looks like a very fine-tuned model, very complicated. You can play with this. And similarly, you have an exact solution. So it's more involved. You need to use some Majorana representation of the spin. But the nice thing is that you can play with these parameters. So if one of the parameters is very strong, in fact, you can see that it maps to the previous toric code model. So in all these three regions, this is the similar phase gapped Z2 phase. So very similar to the toric code. So toric code was this model. The novelty was when all couplings are similar, let's say if they're all equal, then it's gapless. So gapless topological is maybe more tricky to define, but it can be done. What happens when you put a magnetic field? Maybe you can get non-abelian anions, etc. So this was also a very, very big success. Maybe my time is probably over, but let me just flash 5 minutes, maybe not like. So let's take tableau 2. But as I said in the beginning, so the existence of these exact results is really a driving force, because now that we have spin model, which are really Z2, RVB, or Z2 toric code, topological, etc., people are, a big development in the field is to look for material where KIF could be realized, because it looks, as I said, fine-tuned and a bit weird, this interaction, but in some materials, like in the iridates, so there are some materials where it has been argued, even starting from a microscopic model, that a good description could be KIF plus Heisenberg. And then, of course, there's no exact solution anymore, but we can try numerics. So I didn't discuss, but we have many numerical tools for the many-body, like Antoine said yesterday. So KIF Heisenberg is a very big topic in the quantum magnetism field. Maybe, so because just another gapped topological that I like is the chiral spin liquid. If you want, this is analog of the fractional quantum Hall effect, but for spins on the lattice. It was proposed by Kallmeyer and Laughlin back in the days, actually maybe for triangular lattice as well. It was not realized there, but now we have many microscopic models. We have exact solution. We can construct some models. So we either have exact models or numerics. But the phenomenology is the same as the quantum. So we have spin on lattice. It's really like take 2D speed again, but maybe you need chiral interaction or this kind of thing. And essentially, so you have a gap in the bulk, but you have gapless chiral edge states. You know, if you do quantum Hall on a disk, you can have chiral modes. And here is gapped. So this is the picture of the quantum Hall effect, and we all know. And again, it can be fractionalized, excitation, etc. This chiral edge mode has a very particular structure. If I have an SU2 model, I will get some SU2 conformal field theory description. And I need to specify the level of the CFT. So we have models where it's SU2 level 1. So this one is abelian. We have SU2 level 2 now, which is non-abelian. If you know the quantum Hall effect, this is the analog of Moore-Reed. I don't think that Thierry mentioned that on Monday, but this is believed to be, there is a famous fraction 5/2, which is not completely settled yet in the quantum Hall business. So there are proposals for very fancy Pfaffian wave function with non-abelian excitations. We have a spin analog for that. And now even last year, I think there was a numerics claiming SU2 level 3, which is even more exotic. It's analogous to Reed-Rezaei And why it's even more interesting? Because this one allows for universal quantum computation. Okay, so maybe I didn't mention gapless, but okay, I will conclude. So actually, just to show, maybe because we talked a lot about RVB, RVB on bipartite is a good example. If you take this wave function, but now quantum, so if you take superposition of all configuration, and even they can be real singlets if you want, so it's a real genuine wave function for spin model. It has spin-spin correlation are exponentially decreasing. This you expect. This is the idea of valence bond. But if you look at dimer-dimer, so it's not a vector, this one is power law. So this one is called algebraic spin liquid. And again, it's a big field to look for this. So I think my chairman is up, my time is off. So what I tried to address was, the message I was trying to convey was that both for classical and quantum, we have lots of exact results or numerics or good arguments. I didn't touch about the parton construction, but for spin systems, there is a classification in progress also based on parton construction, projective symmetry group representation. I think because we want to discuss open questions, for instance, at the moment, sometimes they claim to have like hundreds of different spin liquids. Even I think I read one paper preparing the lecture where there are 2 to the 21 different spin liquids for the square lattice just by symmetry analysis. It's probably too many, in fact. So is it, what I think is remains to be done in the field is we have, in fact, too many spin liquids, probably. So are they really different? Of course, experimentally or even numerically, can you distinguish them? Because if you have hundreds of spin liquids, let's say, I'm talking, for instance, of gap Z2. In Wen's paper, there is 88 Z2 gap spin liquids. They all have the same entanglement property signature. They don't have any order. How can you distinguish them? So that's, I think, the main question in the field. And then I didn't touch about phase transitions, but it's very exotic sometimes. It's called deconfine, because we have this fractional excitation. They could appear also only at phase transition. Suppose I have a phase transition between a magnetically ordered phase and a phase that breaks lattice symmetries. There was good argument from field theory that the transition could be second order, so not what you expect from Landau argument. And and you could have fractionalized excitation just at the transition. And it's also a search for the Dirac spin liquid that I didn't mention, etc. But so I hope you enjoy, and I thank you for your attention.